Okay, now I'm gonna show the second part, and it's kind of easy if we really understand how the first part works. As the in the second part, we suppose that for some n, we have x belongs to at least c sets ai. C is greater than 0, and the also we have one more condition is the whole space, the mu x is equal to 1, and we're gonna show the mu ai. So the measure of one set is greater than or equal to the c over n for some I, yeah, which is essentially saying that there exists some I such that mu ai is greater than or equal to c over n. So we're gonna do the same thing as we did in the first part. So essentially we're gonna invoke the counting measure again. So we're gonna change the measure into the indicator function, and we're gonna count how many times those AI belongs to, how many times the X belongs to those AIs, and we're given that so every X belongs to at least C sets AI. From that, we can pretty sure that the whole space X is the union of AIs, as it's pretty clear that for each X we have the X belongs to AI for at least some I, right? So we have that equality here, and which would give us the essentially the mu x is equal to mu the union of AIs is 1. We need that information to kind of use the replace the union measure of the union in the part 1. So let's first see how it would work in part 1. So if we have the assumption in part 1, then this would be the summation of the mu ai with no bigger than c, right? As this part would be 1. So now we kind of reverse it. So maybe not reverse, but like do something really similar. Essentially, we're just going to show that this one would be greater than C, as it belongs to at least C sets AI. So basically, we're just use the indicator function and integrate and count. And this side we could write C times the indicator of the union. And basically, if we mimic or imitate what we did in the first part, this part would be super easy. Okay, so suppose we have that. We have this part. And then if suppose there doesn't exist I such that mu of AI is greater than which essentially saying that every AI is strictly smaller than Cn. Then we have n of those sets. So if we multiply n, we would get a value smaller than c, right? Because it would give us the contradiction, this result we've proved. So that's just the proof by contradiction. And also, I think we can argue by dividing those. So dividing n the both sides, we have n over c over n is greater than summation of ai, mu ai over n. And we just pick the max of mu ai as it's finite, so we can always guaranteed find the maximum of the set. And as this one is smaller than the summation of mu ai is, so remember we have n of those sets is gonna be no bigger than the n times max of the mu ai. So now we could cancel n and get the result for just the we can even like be explicit of the I. So I is gonna equal to the index of the maximum of the ai, mu ai. So that's part B.